It's a pleasure to see so many of you here. And I wanted to talk about something that I was never really trained to talk about, and which I never really meant to study, because I think many of you are in the same boat. I'll talk about sort of 4 different projects that all sort of led me to think about this issue of weight gains. And just in case anybody's wondering, this is really not about anthropometry, and it's not about my anthropometry. It's about samples. All right. So, the starting point, and this, even has come up in, Mark, in my most recent paper, that sort of stratified sampling has played an important role in the collection of development data. Some of you who've been out there in the field and, done randomized trials and so forth may not have thought very much about stratification, but it's kind of at our core, I think, among the most prominent data sets that we examined, at least, when I was assistant professor and so forth, and continue to use. Sort of are stratified by income or land holding. So stratification is quite important. The original ICRSAT surveys, they had 40 households per village, 10 from each land category, and that was not representative, of course, of the land distribution in those villages. The ARIS-REDS data, which I've helped to sort of collect and work with and worked a great deal with over the last years, it was also initially stratified by income. There was a process of updating weights. As the kind of keeper of those data, I'm always getting questions about what the weights are. I have some answers, and even trying to figure out what the original people did is a little bit confusing. But the bottom line is that there was stratification. One might argue it's important, and we don't get taught very much about that. Okay. As I say, as I go around, I distribute data, I talk to assistant professor, or even tell people I happen to be working on weights. I get sort of a sense that people think of the weights as a nuisance. They come with your data, there's something your referees can tell you is wrong, but nobody can tell you what is right. And I think that's basically sort of at the heart of the issue, that dealing with weights, there's rarely a mechanical solution to the problem. It depends on what question you're asking, what issues you're pursuing, and so forth. And so the way I'm going to focus this is not to give you a laundry list of how to sort of think about weights from a sort of recipe perspective, but I'm going to talk about 4 projects that, along the way, I realized I had to think about weights, and maybe inductively you'll get a sense of why I think it's important, at least why it's something that we should at least think about, and why it's kind of fun, actually. Maybe you won't believe that, but I really think of these as adventures because, indeed, I didn't start off thinking about weights, and along the way, I realized I had to think about it seriously. Okay, so the 4 topic papers I'm going to talk about. The first is measuring changes in inequality from panel data. Okay, the second will be constructing estimates of economic mobility over multiple generations, again using panel data. A third one will be evaluating changes in spatial distribution in well-being as development proceeds. And the fourth will be looking at the effects of democratization. So some of you may have clues about which of my papers these all involve with, but I don't expect anybody's looked at all of them. Okay, so the first 2 are work that I've done with Sveta Milisheva now at the bank. And the starting point is this issue of how do you construct representative samples from panel data. Okay, so sort of this, we collect these panel data sets. We typically collect samples of households, and we have there's a reason for that. There's sort of a sense that how households are important for resources. We can talk about how households that sort of intra-households is also very important, but to some extent households play a primary role in the allocation of a lot of resources, and it's just easier to collect data that way most of the time. Okay, but when you've worked with, that's like the first time you go in and collect a household survey data, you collect the households, but then you sort of try and go back to those individuals later, and you realize that the households have recombined, and this is something that Duncan has confronted. Any of us who have collected panel surveys have had to deal with. And I've sort of called this, they recombine. These households kind of mix in various ways over time. Okay? And so one of the things that sort of arose as in sort of thinking about this is I have long been interested in the process of household formation and dissolution. And then I've recognized that weights are based on households, and we sample households in some deliberate way. And so one of the kind of questions that sort of arose that maybe some of you think have an answer to, but I never really knew the answer to until I sort of started working on this is the question about whether the fact that the weights are responding to some endogenous variable means we have to worry about the endogeneity of weights in our analyses. Right? And it's not something that none of us ever does, and yet we all use household survey data. Many of us use household survey data with weights, and so I needed a way to think about that. Okay. So all of this work comes from another sort of long-term data sets I've been involved with in some respects from the early 70s when I was in Bangladesh as a child, but although I wasn't collecting any data, I did see the data sites. These are vital registration data from Matlab, Bangladesh. You have the demographic surveillance system, which has 40 years of vital registration data. With detailed censuses in 1974 and 1982. What makes this, I think, interesting is a comprehensive, it's sort of everybody in the population over time. Now, in 1996 and in 2014, we have collected we've done a panel survey, the sort of first economic data that's sort of integrated into the demographic surveillance system. The demographic surveillance system, like many such systems that exist around the world, was really there for just tracking bodies. The basic idea was in low-income countries, you can't measure mortality unless you know what a denominator is, and so you have to have a basic vital registration system in place in order to look at mortality rates and vaccine trials and so forth. So there wasn't much economic data collected until the surveys that we did in 96 and then most recently in 2014. One feature of this, and this has been, it turned out to be, in retrospect, a really dumb idea, is we had this idea, well, the sort of social organization in Bangladesh, households come in baris, which are sort of groups of houses that are related typically. We decided to sample in that way. It turned out that made things a lot more difficult when we actually started thinking about the sort of agenda I'm going to pursue for in the moment. Okay? One of the reasons for doing the 96 survey and the 2014 survey was, in fact, that Matlab is, as some of you know, the sort of site in 1978 of a trial of a family planning and maternal health program that was introduced in 78 and was really, from my perspective, the first program that really showed that providing high-quality services in a low-income setting could result in reductions in fertility. It was not, of course, a randomized trial. It was in 1978. But anyway, that was, it was one of the reasons for collecting the original data, and the subsequent data is to look at that, and I'll talk a little bit about that. But here's the issue that I want to address first, is how do we handle the fact that we have a representative survey in 1996, okay? But we can think about the antecedents of those households in 1974. The antecedents of the 96 households are not necessarily a representative sample of 1974. And similarly, the descendants of the 1996 households that we would go off and interview are not necessarily a representative sample of 2014. And yet, if we want to look at changes in inequality over time, we need to actually turn the panel data into representative samples. So we need to figure out what sampling weights are. Okay? Another thing that some of you may have noticed is we did something a little funny here, at least from the perspective of modern sort of trial literature. We were interested in studying an invention in 1978, and we drew a random sample in 1996. Okay? That, in retrospect, was kind of dumb. We should have taken the random sample in 1974, which we could have done because of the vital registration data, and then followed the households forward, so we would not be so worried about the fact that the household composition in 96 might actually be affected by the family planning program. And that's where this issue that I talked about, we have these households that are endogenously formed as a result in part of the family planning program. We've got weights for 96. Like, does that matter? Okay? So hopefully you'll be convinced I know the answer to that, but I'm not going to tell you yet. Okay? Okay, so, I didn't even really, when we started this, didn't really know how to even think about this problem. I just wrote in a grant proposal, or it was written in a grant proposal that I was part of, said Andrew Foster is going to solve the problem of weights. Okay, so I realized along the way that the key that I needed to take the 1974 antecedents and turn it into a representative sample, and there's this sort of general issue in any of these households that are panel surveys if you want to take a cross-sectional, take a given round of the survey and make it cross-sectional so you can compare sort of cross-sectional differences over time. Now, it turns out that exactly how this works, or the sort of sampling problems that arise depend on the rules. Okay, so when the red survey was initially done, that was really the ERIS survey in the 69-71 period. Then there was a decision made in 1982 to follow up the descendants of those households. Okay, the rule was we were going to only follow those households in the event that either the head had not died or the household had not split. Okay, so in a case like that, assigning weights to the subsequent set of descendants is not hard. Okay. Because there is at most one descendant from every 71 household. Okay? because we don't have any splitting happening, because as soon as the split happens, then we're going to either lose one half of the household, or if the head died, we're going to lose that household entirely. And then the rest of the 1982 sample came from a random sample, was backfilled, so you had sort of sampling weights from 82 that came from the original survey, and then you had a representative sample of everybody else. Okay? In the Matlab Health and Socioeconomic Survey, as is, I think, more typical, is you would do a survey, and then you would try to follow everybody who was in the original households into their subsequent households 10 to 20 years. Maybe people who are migrants, you'd want to follow them. That's certainly perceived as best practice. But certainly people that were in the same area, you would want to sort of follow all the different groups of people. There's a good reason to do that because it maximizes recontact rates, and so you have the maximum number of individuals in both surveys, and for some of our analyses, those differences are going to be really important. But it does sort of complicate this issue as weighting, as I hope you'll understand in just a bit. Okay? But the main point is, in sort of doing these kinds of resurveys, you're sort of setting in motion a different procedure for how to think about weights in a cross-sectional sample. Okay? Now, there's nothing on this slide that I knew up until about a year ago. Okay? So we were kind of working through trying to figure out what the right thing to do. When we knew what the right thing to do was, we actually went into the statistical literature and found that indeed, at least to some extent, some of the ideas that we were working on were ones that were in place. Not all of them, but some of them. But I wanted to introduce you to these sort of two ideas because they're really important, and to some extent they're surprising. Okay, at least I found them surprising. Okay, the first is perhaps not, but it's sort of how it's constructed. It's important to see. Okay, so the idea is that what we're talking about is something that's known in the literature as indirect sampling, where you do a sample of a population and then you reconfigure that population in some way. And so then you have this new sample, and the probability of observing anything in the new sample depends on the original sampling distribution plus the process of reconfiguration. Okay? And we sort of all know what to do if we do if we just do a cross-sectional survey and we have probability weights. There's some notion that we kind of use as a weight, the inverse of the probability. And one way of thinking about it is that's where this comes from. This is the Horowitz-Thompson estimate. Okay? And the basic point is, imagine you're interested in a quantity, the sum of yi in a population, okay, and you have a sample, okay. Well, then you can have an indicator I, which tells you who's in the sample and who's not. And for every person in the population, in principle, but you don't really need that, you have pi I, which is the probability that that household was sampled, okay. And so you construct this thing, the sum of yi times big I over pi I, okay? And the whole point of the Horowitz-Thompson estimator is simply if you take expectation of that, you can bring the expectation inside, so you've got expectation of II. What is the expectation of II? Well, that's simply pi I. And so you're going to get pi I over pi I, so that's going to give you sum of yi, okay? And so what's sort of neat about that is because you have this II in the first expression, you only need the y's for the people in the sample. You don't need to worry about the y's for everybody else, and yet you can construct an estimate of the population level. Okay? And notice this does exactly what you think you would want to do, which is take the probability of sampling and take and invert it and sort of add it up to get weights. Okay? The only complexity is, well, then how do you calculate pi I in the case of indirect sampling? Okay? Well, basically, you just need to kind of work through and say, okay, well, I had some original sample. There's a probability that people were sampled. And then I can follow up people later on. And if we think about these households, and I'll go through an exercise in just a minute, every household is composed of people in the initial sample. So the probability any subsequent household is in your sample is going to be some combination of all the probabilities of the people who live in that household at that point in time. Okay? So that was one thing. Now, the second thing, and again, I'll illustrate this with an example in just a bit, is that there's this fundamental problem, and the best way to think about this, if you're familiar with something like the PSID, in the PSID, right, there's an initial sample of people. The households were interviewed subsequently if there were descendants of the initial samples that were there. Okay, the probability of sampling of that household depends on a bunch of stuff that isn't known. Okay? Because the probability that PSID household was picked depends not only on the particular sample that was drawn in 1965 or whenever the first sample was drawn, but on all possible samples that could have drawn in 61, because there's some sample that it would have brought in the wife instead of the husband. Okay? So it would seem like to construct the PIJ for indirect sampling, you would actually need to know the probability that every single person in the household is a descendant of someone who could have been in the original PSID sample. Okay? And that is something we could never know. Maybe in Sweden you could know that, but you could never know it in the US. Okay? But it turns out that there's a little bit, it uses the same kind of trick, and I just wanted to show that I probably won't explain it, do it quite justice, is that you have a set of people, descendants J, who are in some, who belong to the descent you have a household I in a particular period. You have a set of antecedents of that household, and basically you can construct this thing, which is gamma j times ij over pi j, which is the probability that any particular individual is in the sample. Okay. And as long as these gamma i's sum to 1, and this will be clear in just a moment, you can still construct an unbiased estimate of the sum of yi's. Okay. So let me just show you how this works. So here's an example of what we faced in the context of Matlab. Okay? So as I said, what we did was we had an original sample of people, okay? And we had this Bari level sampling, okay? And say, just for the stylized example, we had a 50% chance of sampling this Bari and a 50% chance of sampling this Bari, and we sampled one household per Bari. So if we got this household, if we got this Bari, we would pick one of those three. So the original sampling probabilities of A, B, C, and D are 0.167 up to 0.5. Okay? Then, if we think about the 2014 sample, okay, there's a series of households that are all descendants of the blue households. Okay? And the question that we would like to ask, the pi ij that we would want, if we want to turn this into a representative sample, is we need to know the probability that this household ends up in our descendant sample. And the question is, what is that probability? Okay? Well, the probability that this guy's in the sample depends on the probability that any of these three links was chosen, which is simply the probability the first Bari was chosen, so that's got to be 0.5. Okay? Similarly, the probability this guy's chosen is going to be 0.833 and so forth. Okay? So the probability of a particular household being picked depends on the full set of links and the full probability distribution over the initial population. Okay? The problem is that in a normal data set, you only picked one of these households. Let's say this guy. Okay? So you know 0.167. You follow that household and you end up with this household here. Okay? And you might be tempted to say, well, the probability of sampling this household is 0.167, so maybe the probability of sampling this household is 0.167. But that would be wrong. Okay? In order to get the right number here, you actually need to know, if I pick that household, would that household be picked? And the answer is yes. And if I pick the third household, would I pick a household that would be that? And so forth, right? To get to the 0.5. Okay? So what I want to convince you of is that it would seem like this is an impossible problem, okay, in a normal panel data set, because we only know about this household and this household. We don't know about these links at all, because household B wasn't sampled at all. Okay? Well, this weight share estimator sort of uses a little bit of a sort of a funny thing, or a little bit of a trick, because now think for a moment, if in one state of the world I pick A, and so I might assign a particular weight to this thing of 0.167. Okay? On the other hand, in another state of the world, I might get 0.167, in which case I would also assign a 0.167. Or I could get this state of the world, and I'd also assign 0.167. Okay? In other words, in different original samples, I'm going to get different households. So I can ask, what is the expected weight? In other words, each weight will be wrong, but the question is, on average, am I right? Okay? And the shared estimator says yes. Okay? So how does that work? I mean, in this case, it's kind of an interesting one because it's 0.167 times 0.167 and so forth. Okay? The only trick is that the weight you want to assign here, okay, is the weight, which is 1 over 0.167, divided by the number of links, which is in this case 3. Okay? And how is that going to work? Well, so 1 over 0.167 by 8 or 9. Okay, we're going to divide by 3, like 2. Okay? But we're going to take that, see, 0.167 is in the denominator from that calculation. What's the probability of that weight being realized? It's this, 0.167. So the 0.17 is cancel out. Okay? And so it turns out that that happens in each state of the world, and so it turns out if what you do is if you figure out what the probability of this thing is, which would be 0.167 if you picked up this household, and you divide it by the number of links, then on average your estimate of the weight would be right. Okay? And that's the shared estimator. And it doesn't actually have to be 50-50. There's other tricks, and we've done some other work. But that's the basic idea. It's a little bit remarkable. But in order to better understand, yeah, go ahead.
So the links that you're dividing by are in the second period? The number of links in the second period?
Yes, these 3. Now, it's a good point because it does suggest you need more information than you typically have in the typical panel survey, right? Most of our panel surveys, you can't actually ask our 2006 households, or we don't usually ask our 2006 or 2012 households, like, of your descendants, which ones could have been in the sample that we did in 1996? And you could ask them, they would probably laugh at you, right? But in principle, that information will be available, and in vital registration data, it is available, okay? Well, it's worth sort of thinking about this a little more concretely by talking about the PSID, okay? Because for a long time, we couldn't figure out what the PSID was doing. And what they're doing is a lot like what I just said. They have this, when they put it together, they have this idea, we're going to use the like marries like solution. Okay? The basic assumption is you have this descendant household. You have a man and a woman. Let's say the man is the guy with the PSI DNA. Okay? He's the guy who makes the household become a PSID sample. Okay? We know what his weight is. Oh, sorry. Yes, you're recording. Okay. I guess I'll have to, I never do this, but is there a pointer? Or I'll point with a mouse if I need to. Okay. So then the idea will be, what we're going to do is we're going to assume the husband and the wife are the same. Okay? Now, we know the probability that the husband was included in the sample because he comes from the PSID lineage, and the people have been calculating statistics about that guy since he was 12, right? And we're going to assume he married someone just like him. Again, that seems like a crazy assumption. Okay, because, yeah, we kind of marry people like us, but we often marry people who are a little different from us, too. Right? It's a little boring to marry someone just like you. Okay? Anyway, that's the PSID assumption. Okay? And what I sort of work through and say, well, under what conditions does that actually work? Okay? And the sort of the whole point of this little exercise, okay, is that we can, that this works as long as the probability of being picked is really small. And that's a really good assumption for the PSID. It's like 4,000 people out of the entire population of the United States. Okay? So the idea is you can kind of figure out what the sample weight is by essentially saying, if the husband is P and the wife is Q, if we actually knew the wife and the husband's probability of being in the original sample or their antecedents being in the original sample, okay? We can write down an expression, and we can approximate that. It's something like 1 over Q plus P plus Q, and then it has this other term. Okay? So this would be if we did it right. That is, we actually knew the husband's probability and the wife's probability, and they were different. Okay? The other alternative, however, okay, is to essentially make the assumption that that the husband and wife are going to be the same, okay? And basically, the expression here works that out. What if you make the assumption that the husband and wife are the same? You assign the wife the probability that the husband has and vice versa. And you realize that sometimes you get the husband and sometimes you get the wife over different draws of the PSID sample. And it turns out you get this expression if you do it the wrong way, assuming like marries like, and you get this expression if you actually had the information. And the point is, at least to first order, these things are pretty close. As long as the sample size is small, you can use a like marries like assumption and not worry about it too much. And the reason it works is your weight is wrong for every household, but on average it's right over draws of the sample. Okay? Now, it turns out that that didn't work for us for a number of reasons. The first is that we wanted to go from 96 and go backwards, okay? Now, there's an advantage in going forward because we all have two parents, okay? But we don't all have two children. A lot of people do, but not everybody, okay? So if we all know that, that I had two parents and my wife had two parents, and so we can kind of figure out that the number of links in our household is going to be, at least if it's a simple nuclear household, is exactly 2. It's always 2. But if you go the other way, you have to deal with the fact that some people have 3 kids and some have 1 kid, and so it's not nearly so obvious how to proceed. So that doesn't work. Okay? Our sampling is not necessarily independent, which is sort of an assumption in there. Our sample is not a small fraction. And there's also a sticky issue, and this arises with the PSIT too. A substantial fraction of people are not in the frame. That is, the calculations, the assumption I was making only made sense if your wife's antecedents could have been in the original PSID. But in fact, if your wife is an immigrant, there was no way that she could have been in the original PSID, and so you shouldn't be dividing by 2 in that case. And we have a lot of those because we're dealing with marriages that go across borders. Okay? So now let me show you what we did in fact. Okay? The first is to understand the data. We have this longitudinal data. We have data at every point in time on who's living with whom. Okay, this an understructure for the household survey data we have at, in effect, 3 points in time. Okay, so what we're going to do is we're going to create links between households based on people. Okay, so the idea is that if we have a household in 74 and somebody in that household is also living in a household in 96, then those households are clearly linked, okay? But we can also imagine a case where someone in 74 lived with somebody who then is in a 96 household, and that's what we're going to call a first-order link, and so forth, okay? So we're going to create links based on residence. So all of this linking that we're doing is based on residence patterns, not on relationship data. And we can talk a little bit about whether that's the right thing to do. It's what we did, and I think there's good reasons to do it, okay? Now, it turns out that because we did it that way, there's a nice little analytic structure that we can use. Okay? So we have a set of households in period 1 and a set of households in period 2. The set of households in period 1, we can take the people A, B, C, D in period 1 and partition them into 2 households, alpha and beta. Okay, that's what this matrix is. And in period 2, we have some of the same people and some new people, and they're partitioned into households. Okay? And we have another matrix which maps the people at time 1 into the people at time 2. Okay? That's really all we need in order to create these links. The first matrix we need is we just take our household matrix, our partition of people into households, and multiply by itself, and we get something like this. This says A and B live together, and C and D live together. And there's a comparable one at time 2. Okay? And then we can construct this C1, P1, C2 matrix. Okay, so those are the co-resonance matrix, the sort of matrix that maps people into people, and the co-resonance matrix again. And now we get a set of links between people in 1 period and people in 2. And the thing that I want you to recognize is that Mr. A is now linked to Mr. E. Okay? Why are they linked? A and B live together, and A disappeared by the second period, but A lived with B, and B later lived with E, right? So this mathematics works out. So this now describes how people are linked across time. And then if we pre and post multiply by our household variable again, we end up with this matrix that relates households at different points in time. So now we have a matrix that links households at 1 period of time to households at another period of time, accounting for all the possible resonance patterns as they happened over time. Okay? This is what it looks like in practice. Okay, this is from the Matlab data. And the thing that was very striking to me about this is 74 to 96. And it's one of the reasons we didn't want to just use relationship data to link households. These households tend to be, they're not that complex. Okay? Maybe there's a mother-in-law and maybe a couple of brothers living together occasionally. But it's not like they're not huge households. Nonetheless, there's a lot of shifting of co-resonance that happens over time. So if you want to take a set of 74 households, just yell at me, I'll go back. It's like my dog. All right, I'll learn eventually. All right, so the sort of point is that this 74 household has a lot of 96 links. Okay, now why is the density of this matrix going to matter? Because the denser the matrix, the more the 74 and 96 samples, the more you're going to need to reweight in order to get a representative sample. Why is that? Well, take this household, DO1. He has 11 households in 96. Therefore, in a simple representative sample, he has 11 chances to be picked. Okay? So DO1 in the 74 sample is going to be way overrepresented relative to everyone else. Okay? So if this was just an identity matrix, we'd all be fine. We could say, okay, we just take the 96 weights, or even if it was just random sample, we take just one, and we apply it to 74. But because different households have a different number of connections to other households, when you do this process of linking 96 to 74 households to get the set of 74 antecedent households, you're going to get very heterogeneous weights across households based on the number of things in a row. And the same thing is going to happen when you go from 1996 to 2012. Okay? If you have a lot of co-residents going back and forth, you're going to get very different weights in 2012 than what you would just get by taking the 96 weight and moving it forward. Okay? So then the question is, well, this pi ij, this is the weight we need in order to construct this 74 probability of being sampled and the 2012 estimate. Now the question is, how do we get it? Okay? So, and the answer, it turns out to be fairly straightforward because we're working with demographic surveillance data. Okay? And because we were the ones who actually drew the sample in the first place. Okay? Because what we can do is we drew the sample in 96, and that yields a certain set of 74 antecedent households. But we can rerun that survey, that sample, a million times. It's just a computer exercise. And each time you run it, you get a different set of 74 households. You can count up how many times each household appears in the antecedent household, and that's your estimate of pi ij. Okay? And the point is, you could never do this analytically because of all the dependents. Different people are likely to be living together or not living together, and so forth. These are not independent draws. But because you have access to the full set of links and you have access to the sampling frame of the original survey, one can actually construct the antecedent probability weights and then construct representative weights, and one can do the same thing going forward to the later sample. Okay? Now, one thing that I said, or that I sort of raised, and maybe some of you have the answer, okay, is, well, these weights, they're clearly endogenous to all these co-residence decisions. Can we take them as given? Okay? Well, first I want to show you during using a little, some of you will sort of recognize this problem immediately, but let me just show you a little stata simulation. Okay? So I'm going to generate a random variable, generate an independent x, and generate a y. Okay? Hopefully you've all done this before. We're going to construct a sampling probability that's based on the endogenous variable. Okay? And I'm going to show you that, in fact, the endogenous variable is correlated with the sampling probability. Okay? So here's our problem, right? And the question is it a problem? Well, first, I'm going to regress y on x in the sample. Okay? And remember, the true coefficients were 1. On x was 1, and the other one was, I think, 0. Yeah, 0. Okay? And obviously, if you don't use weights, you get biased estimates. Okay? You regress y on x only in the sampled data, you don't get the right estimate of the coefficient on x. Okay? But if you do use weights, that's the bottom panel, you get it bang on. Okay? So the fact that the weight is endogenous with respect to the outcome variable does not present a problem as long as you use weights in the estimation. Okay? Now, some people may know this result. There's a literature on choice-based sampling. It fits exactly into that context. Why does it work? Well, the reason it works is because the randomness associated with whether someone's inside the sample, conditioned on their probability, which is observed, is all about sampling noise. And that's true random noise, right? It's not like the choices that people make. It's true random noise. And therefore, that noise, whether you got included on the sample conditional on your probability, okay, that noise is uncorrelated with anything, right? The sample is being drawn on top of all this behavior stuff, but the sampling probabilities are not correlated with them at all. And that's basically what the formalism says. If you just think about the sort of the relationship, the XI-EI, what you would need to construct in order to find the bias of an OLS estimator, okay? Well, you want to multiply it by the II over pi I that we've seen before. You can take expectations through, and you get exactly the population and estimate of xi, ei. So as long as the population, x and e, are not correlated, when you use the sampling weights, they're not correlated as well. Okay? So this thing that worried about me, that I worried about for 30 years, turns out to be not true. Okay? Hopefully none of you had to worry about that. Okay? Doesn't matter. Okay? Well, here is just, so here's one variable distribution of household size with various kinds of weights. Okay? Since this is a vital registration data, and we have household data for the entire population, 74, we know what the truth is, but we also know what our sample of antecedents looks like. Okay? And so we can actually see how things line up. So the actual population is the black. Okay? The population weighted is what I would call the right thing to do, okay, which is to do it the way that we did it by simulating these links and so forth. And you see that the red and the black are pretty much on top of each other, okay? Now, all is not lost. The green curve is doing another thing that you can do if you don't have proper weights, which is basically to run a logit. If you have the you have the 74 census population, you know which were in the households, and you have observable attributes that are both in the census and in the household, you can do a predicted probability of being in the survey. Okay, and that's the green line. It also works pretty well. Okay? But the other things that you do, if you just use it unweighted, you're obviously biased. Okay? You have two big households. Why is that? Well, big households are more likely to split, so they're likely to be overrepresented in the subsequent sample. And if you do kind of the standard thing of assigning the weights based on the original household, it doesn't fix things at all. Okay? So this is just my graph to say all that work maybe was worth it. Okay? So I think, and then this is, birth data. Okay? Again, in some ways there's no reason to use the weight data for this. I mean, the birth series is published by ICRB. But there is a problem, which is ICRB, that has the Matlab data, they have vital registration data. They know everything about everybody for 40 years. They will not release that to anyone, no matter what kind of clearance you have. But they allowed us to link data that was linked to the people in our survey. Okay? So the question I'm asking here is, imagine you only had our survey, and you wanted to construct a birth series. Could you replicate what actually comes out of the data? And the answer is yes. If you don't use weights, you get the green curve. You're way off. But you use these weights, the black arc curve is the blue one, and the black is the truth. They're pretty close with a little more noise. Okay? And then this goes back to the original question I started with. Okay? And this, in the paper itself, there's a whole motivation of what we're actually looking for here. But this then takes our measure of the distribution of educational z-scores at 3 points in time in Matlab over a period of tremendous economic and social change between 74, when George Harrison had a concert and everybody thought Bangladesh was a disaster, to 2012, where it's sort of considered a place where has been extraordinarily effective, at least in basic human resources, and the economic growth is plugging along despite the political mess. Okay? And so you see, not surprisingly, a shift up in sort of educational, the educational performance of the kids. But the interesting thing that we sort of point to in this paper is that the variance doesn't change very much. Okay? And this relates to a sort of the paper, the fundamental question that kind of drive this paper, is that to what extent does fundamental investment in human resources, which Matlab in particular and Bangladesh in general has been very good at, lead to a compression in outcomes? And I think the answer from this graph is no. Okay? And then I'm not going to be here to kind of debate through all that, but anyway, that's a substantive point of that paper, which I refer you to. Okay? So that's sort of what you have to do to cross-sectional estimates. Okay? And it's just, it's required us to think a lot and provide us some new insights in how weights work. Okay? Now, what about mobility? Okay? So we have panel data, so in principle we should be able to look at mobility. But we have a problem, it's a little bit of our own making, okay, which is that we did this survey in 96. We want to go back and create a 74 representative sample. And then we would like to know how well the people who started in a given 74 were doing in 96 and later in 2012. Okay? Now, if we'd actually started with a 74 sample, that would have told us who to interview in 96 and therefore who to interview in 2012. But because we went backwards and forwards, okay, not every household in the 96 sample that's a descendant of any given 74 households is going to be in the survey. Okay? So we have another problem to fix. Okay? Which is the fact, what do you do if you only have a sample of the descendants from the original sample? And that sample, in our case, is being driven by the fact that our original survey was done in 96. Okay? Now, this leads to questions, to a sort of a fundamental set of questions that I think we all should be interested in about, like, if we're measuring economic mobility over time in a developing country, like, what are we interested in? Okay, what is the right concept? So, you know, when you're looking at mobility, or economic mobility over time, it's kind of nice to think about individuals because that's not very complicated. You have an individual at one point in time, see how they're doing, look at them 8 to 10 years later, see how they're doing. Did they go up? Did they go down? It's a well-defined question, but when you're talking about 40 years, it's a silly question, right? We probably don't really care so much about whether someone, you know, they're earning when they're 20 versus they're earning when they're 70 or whatever, 60, if I do the math right. Okay? So individual well-being is not really a great way of thinking about 40 years of economic mobility and perhaps how it's affected by access to health and family planning services. A more standard thing to do is biological descendants, okay? And this is a very natural thing. You take the 74 given sample and you look at their kids and you look at their grandkids. And, you know, my colleague John Friedman's doing that using, you know, the wage data in the U.S. And, you know, I don't want to be too critical as a result. However, I think there is a fundamental problem. It's not well suited to what we're trying to do, because the problem with descendant surveys is they're asynchronous, right? We all know somebody who's like, where an uncle is younger than their nephew, right? That people get out of sync. So if we start with a given set of households in 74, and then we ask, like, what's the state of their sons in 2012? Their sons will be lots of different ages and therefore experiencing lots of different things. Okay? So then you have to kind of figure out how to factor in age or assume that age doesn't matter. You have to do something to kind of finesse that. Okay? It also, from my perspective, doesn't work very well when there's a lot of people living with you who are not sort of direct lineal biological descendants, your brother, daughter-in-law, and so forth. Okay? So what I wanted to think about in terms of sort of dynamic change is the population of households in a particular region over time. Okay? So we have a given survey in 74. We have another survey in 2012. We have a set of links that link 74 to 2012. I would like to know a given household in 74. What is the distribution of outcomes of their descendants in 2012 based on a particular set of rules having to do with co-residence that I've talked about before? So that's what we're doing. You may like the other ones, but that's your problem, not mine. Okay? And so this is what I was saying, that in fact we're going to have this sort of a problem of non-random sampling of descendants, and we have to kind of figure out what to do. Okay? Now, to give you some sense of this, okay, here's a little stylized, model. Okay? So we have two descendants, and if we observe both of them, we would say their average income is y1 plus y2 over 2, right? And that would be our measure of mobility, my income relative to the average income of my two sons. Okay? And if the sampling is independent, that's going to work fine, because sometimes we'll get y1, sometimes we'll get y2, sometimes we'll get both, but the average across all states of the world is going to be still y1 plus y2 over 2. Obviously, it'll be noisier if I only get one son, but on average, we'll get one son or the other with equal probability. Okay? But if the sampling isn't done independently, which is not in our case, okay, it may well be that maybe two states of the world observe. Either you observe y1 and y2, or you only observe y2. Okay? So in that world, the average of my descendants in the sample is not going to be y1 plus y2 over 2. Okay? It's going to be a quarter y1 plus 3/4 over y2. And if the sampling is correlated with the income of my kids, that's going to be a problem. Okay? And so we have to kind of figure out, well, what are we going to do in a case like that, where we're not going to have necessarily a random sample of our descendants, and we have to fix the problem. Okay? Well, this is another, I'm going to call it adventure. Maybe you aren't convinced the last one was an adventure. Maybe this one will strike you as an adventure. And it became quickly clear to me that there's lots of things you could do. And so I wanted to see, well, is there something that you could do that's basically right, okay? So, in other words, like, how are we going to pick the weights in different states of the world on my two sons so that on average I get the right income of my sons, and which I want that result to be fairly robust in some sense, okay? So there's one equation that basically says the expected value of whatever I do in terms of weighting my two sons has to equal y bar. That would be a necessary condition. And the other thing is we'd like the variance to be small, okay? And so I wrote down the variance, and it became pretty quickly clear that there's no way we could solve this thing for W1 and W2 because it would depend on Y1 and Y2, and if you knew what Y1 and Y2 were, you wouldn't have a problem to begin with, okay? So I sort of mucked around a little bit, took a couple of derivatives, thought maybe a derivative would be a good thing because we want our results to be not very fairly robust to the different values of income. So I ended up with this criterion function, which is that the derivative doesn't change very much. The second derivative is not very large with respect to the income of the first and the second son, and that the expected values work out. Okay? So I did this maximization, and much to our surprise, we ended up with this very simple formula, which the weights you should apply should depend on the original the 96 probability of sampling a household, probability of I, which is the probability of the original household, which we've calculated in ways that I talked about before, and n, which is in this case the number of sons. Okay? So this is what I got. Okay, this should look familiar to you, or it should ring a bell. This is actually the weight share method. Okay, I came up with it, but of course then I realized almost everybody knew that. Okay, at least within a certain class of people. So in any case, we came up with this sort of estimate, and then we're able to sort of formalize it, and then use that to look at various definitions of mobility weights. Now, one of the things we were kind of interested in is, well, all right, when is it a good thing to use this procedure, the weight share method, which we know has some potential problems because we're basically sort of, we know that on average we're right, but in any particular case we're wrong, versus doing something else like just taking the average income of my kids, recognizing that occasionally I get a biased estimate. So we set up the little simulation exercise where you have 3 states of the world, and the 3 states of the world are sort of generated by this thing, and the parameter delta tells you how correlated the probability of sampling is with income. Okay? So we ran these simulations to get some sense, okay, of, well, what would happen to our estimator based on as the correlation between sampling probabilities and incomes changed. Okay? And the green is our weighted estimate. And the good thing, which is what I built into my maximization, is that it's fairly robust. Okay? The green line doesn't move very much as the sort of the correlation between income and sampling probability changes. Okay? The red curve is if you use no weights, you just do what you might normally do, which is let's find all the descendants we have and to calculate their income and use that. That works great if delta is very small. There's no correlation between sampling probability and income, but it gets really bad if there's a high correlation. Okay? So, here's the graph, gives us some sense. Now, you might ask, well, where is your data? Okay? And this is one of the most disappointing answers to questions that I've ever had to give, which is it's right here. It turns out that the sort of correlation there is a correlation between incomes and sampling probably in our data set, but it's exactly where it doesn't make any difference at all. Of course, we didn't know that until we did it right, so I'm a little bit justified, but anyway, it's just a sort of a fact. Now, the other point that's worth saying is that, as I suggested, there is a real problem with using the weight share, and this is something we all know about using weighted data. It tends to increase variances, and indeed, when you use the weight share methods, the variance is much, much higher than if you just do the other. Okay? All right. So we now have a procedure where we can actually see what happens if we use population. Again, we have to use household size or dependent variable because that's something we can actually take from the vital registration data so we can check and see if our approach works. This is a regression of household size change between 74 and 96 and a series of initial conditions. I wouldn't worry too much about the specification or why it's there and so forth. The main thing is we can use our formal approach and that, these estimates end up being pretty close. Yeah?
What are you doing about the level of the bias?
So in the previous graph, we just taken it out. That's kind of here, right? And so, we're not doing a mean squared error here. This is just the variance of the estimate across draws. But you'd want to put them both together, I think is what you're getting at. But you'd have to combine, in some sense, two graphs.
Well, actually, what I was asking.
Yes, okay.
It's even simpler. So if we go back to the previous.
Yep.
So I think 2, there's still a level bias.
Oh, yes, there is still a level. Let's see. Yes, and I think, I can't right off the top of my head remember what that source is or where that came from, right? Because
but you can remove it.
Yes, you can remove it. Yeah. Okay. So anyway, the main point is that the sort of formalism does mimic the population, which is after all what we're after, right? We're trying to see if we have a survey data that's a sample. We'd like to replicate what we'd do if we had all the data for the population. Okay? So here's an important point because replicating what you get for the population is not the same thing as replicating the population of any particular coefficient. Okay? So there's a paper that some of you may know in the JHR, What Are We Waiting For? And it makes the point that using weights when you're estimating regressions doesn't always replicate the population average of a particular quantity because it depends on essentially the variance of the x in different populations. Okay? And so I haven't solved that problem. I've said, well, that's not what we care about. What we care about is replicating what you would get if you had the population data. And this we can do. Okay? So that's the idea. Happy to talk about that later if anybody wants to understand more subtly what that's all about. But there is a difference between replicating what you'd have if you had population data and getting the population estimate of a structural coefficient if there's heterogeneity in the population. Okay, well here is just sort of the payoff. We're able to construct these educational mobility graphs between 74 and 96 and 74 and 2012. I've stratified here between villages with high education in the first period and low education just to see if sort of village characteristics matter. And so, this looks like probably any other, most other regressions you've looked at with sort of outcomes at one period on outcomes of the other, which is what this is, so that shouldn't be a big surprise. The key substantive question is sort of how flat this curve is, which is a little misleading because you have to look at the axes, right? And the basic point is that sort of a 1 standard deviation difference in educational attainment in the first period is translating 14 years later or so, or 12 years later into about half a standard deviation. So there is sort of, some mobility, you would say, some compression of the educational distribution, or not compression of the educational distribution, some mobility where the relatively well-off people are moving down relative to the poor people, except everybody's moving up. It's just a matter of the poor people catching up a little bit. Interesting, if you look 74 to 2012, the sort of original village conditions sort of disappear, and you see even more sort of compression. Now about a 1 standard deviation in 74 is connected to basically a quarter of a standard deviation period later. So this is a period in which in Bangladesh, over this period, 74 to 2012, at least in terms of educational attainment, there seems to be a lot of mobility, okay, in the sense that the sort of the outcomes in 2012 are being drawn not so much from a stratified distribution, but from sort of an overall distribution. And that's consistent with the idea that this is a place that was very successful in implementing health and family planning programs and education. Yeah? Okay, so what I did is I asked the right question, okay? And that's important, right? Because if so what I was thinking about is, let's think about household mobility within the Matlab area. And so the only households that count are the households in 74 and the households in 2012, okay? Why is that? If you think about it from a national perspective, we do that all the time, right? We're interested in the effect of a program on our country, and if people leave or people come in, maybe, whatever, we care about the citizens of our country. Or if we're thinking about voting, right, the people who vote for us are the people within our country, and so we care about mobility within our particular geographical region. Obviously, that's kind of a rogue's answer, right? The problem is trying to think about these issues of constructing the correct sampling weights for the out-migrants is a real headache. Because for the people inside, we actually know, who their antecedent households were, to the extent they were within the area, but at least we know who's in and who's out. When somebody leaves, the antecedent households come from everywhere. We have no idea how to think about those sampling probabilities, right? Or perhaps we just say it's the sampling probability when they were in the region. We just apply it to that because the other people couldn't have been in the sample at all. But there's always a possibility that somebody else from the Matlab area moved to Dhaka, and then they got married, and now there's actually 2 chances that house will be in the sample. So it's just a mess to think about it that way, and I prefer not to. But I agree that if you really want to evaluate the effect of a program on people, you need to do that. If you want to evaluate the effect of a program on space, it's not so much a problem. Okay. Now, this is Matlab, so just to show you about the treatment comparison. Everything else was stratified by education, but here's looks at the treatment area, the comparison area. And interestingly, if you look at 96, you see the treatment area, there was higher education, right? This is something that we've known, and it's gone over some time. If you look at the same mobility graph by 2012, it's gone. Okay? It turned out that the educational differences that accrued to the areas that had access to health and family planning programs in the mid-70s showed no differential benefit in the latest round of the survey. This is not the point to get into that, but again, just to show you that we actually used this stuff. And the reason that I got into all these weights is because I wanted to know the answer to that question. Okay? All right. So I think I have 15 minutes. Is that about right? Okay. So let me just I'll rush through the last 2 just to give you a sense of what matters. I can do it fairly quickly. This one here is about segregation. Now, I have to apologize, this is actually not a developing country, except you think of the U.S. as now a developing country. However, I am going to use it for a development purpose in just a minute, so I need to set the stage a little bit. But the point is that when you're measuring income segregation, it turns out that sample sizes matter and weights matter, and I want to make that point. Okay? So there's sort of a bit of a debate in sociology about whether income segregation in U.S. cities increased over the 2000s. Okay? And my co-author sort of thought there might be a problem because over that period, we went from using the long form to the ACS as a basis for measuring income segregation. And that meant that the sampling rates went from 5%, from 17% or so to 5%. And the idea is when you're measuring segregation, sample sizes matter for bias. Okay? Let me help you understand this. We're talking about income segregation. So imagine you have a city and every census tract has exactly the same income distribution. Okay? But you only sample 1 person per tract. Okay? And now you try to measure income segregation. Okay? You will find out that this is a really terribly segregated city. Right? Because you'll draw from a different point in the income distribution in each tract, so these tracts will look really, really different. The more people you sample per tract, the closer you will be to finding out that, in fact, all these tracts are exactly the same. Okay? And it turns out on the order of 5 to 17% actually makes a big difference. And so at least the possibility arises that the perception that income segregation in U.S. cities is rising turns out to be an artifact of something that happened at the Census Bureau. Okay? So, I've sort of already gone through that. I won't take you through all the details given the time. There are a couple of different measures. It turns out that one of the favorite ones to use is called the entropy index. And it turns out that for correcting sampling bias, that there's something really nice about that, which I'll show you in just a minute, which is this. Okay? So the entropy is just this way of transforming the proportion of people who live in tract A that are below the sort of 10th percentile of people in the city, right? And you put all that stuff together, you get a measure of income segregation, okay? So it turns out that if you just think about counts and you ignore weights, that the bias correction turns out to be just 1 over n, 1 over the sample size in the tract, okay? And it turns out that the tract sizes in the U.S., in the ACS, are on the order of 50 or so the bias ends up being about 2 points. And that turns out to be about the level of the change that you see when you look at income segregation. Now, we did all this before we went to the RDC. When we went into the RDC, okay, here's the adventure part, we realized that this correction for sample size wasn't enough. Why? Because we'd ignored the fact that the sample sizes were used in a weighted way to construct the grouped estimates. Okay? When we get grouped estimates of the income distribution of a given tract, okay, those are based on a tracked sample of a certain size, but also those households are differently weighted. Okay? And one thing we also probably know, or you probably know, that more variance in weights is a lot like reducing your sample size. In the extreme case where one household gets 1,000 and every other household gets a weight of 1, it's basically like you have a sample size of 1. Okay? So it turns out that we could actually work out a bias correction that works with weighted data, which is the sum of WI squared, which is going to be the same as 1 over n if the weights are all the same. Okay? So anyway, here's another case where thinking about the fact that the underlying data are weighted really mattered. Okay? We were able to show that our bias correction on this is data from 1940. The advantage of 1940 is we actually have data on everybody. Okay? Here's the estimate if you don't correct. Here's if you correct only for counts. And here's if you correct for weights. And if you correct for weights, you're unbiased. Okay? And this is, substantively, this is the US. It says if you looked at the raw white estimate, it's marginally increasing, at least over the relevant period, over 2000 to 2010. But if you look at the white, the true estimates, it actually is going down. It's even worse for blacks. There's a big increase and a very small increase. And you look at the data. Why is that? Well, because the number of blacks who are sampled in the tract is even smaller than the population. So these measures of income segregation among racial minorities are even worse than the ones for whites as a whole. So anyway, this kind of tells the story. It basically says, as you go from using group data to using using RDC data, to using count-corrected data, to using weight-corrected data, what happens to your estimates? And the answer is essentially that everything seems to, the bias always seems to be in the positive direction. Okay? Now, where's the development payout? So the development payout is going to be, okay, well, another question we might think about is development. This is Matlab over 30, 40 years. How does the income segregation change? So we might have one view of development that even within a region that in the process of development, some areas will become more, have higher incomes or higher consumption. Other areas not so much. They'll be catching up. The sort of notions of Kuznets that creep in here. That is, this idea of spatial variation in income is exactly the same as income segregation in the US context. So I took our estimates, the raw estimates, the count-corrected, and the weight-corrected estimates for this entropy index of education across villages in Matlab over time, okay? And you get a really different answer if you deal with the weights, and even with the counts. With the raw data, there's an increase through 96 and then a decrease in the degree of segregation. This is education, the extent to which there's sort of variation across villages in education. But if you do the corrected estimates, it was pretty flat, and the segregation only started to rise when you got to the last round of the survey. Okay? So weighted estimates really matter here in terms of an answer to a question that I don't think has been asked enough in the context of sort of development, but which if we're going to use household survey data to look at segregation or to look at spatial distribution of income growth, which is in some sense the same thing, we're going to have to account for weights. We're going to have to affect for sample counts. We can't use the sort of general idea that we often rely on that, well, sample sizes, the expected values are right. Here the expected values are wrong if you don't think about the underlying distributions. Okay? This is per capita consumption. Let me not talk about that. Okay? Don't really have time to talk about the last example, but just to tell you, it's another example of weights that crept into my life without me wanting to. Okay? Peter Delbo and myself and Louis Putterman have a paper in a lab looking at democratization. The sort of idea was, can we show whether there's a democracy effect? Can we establish a democracy effect? Accounting for the fact that when you give somebody democracy, they choose different policies. And so we needed effective democracy net of the selection into policies. And we devised a procedure in 2010. And then we were thinking about doing some more work, and we realized, no, we can just solve this problem with weights. And so we did. Here's just the bottom outcome. I'm not going to take the time to explain it, but the basic idea is the original data. The idea is to what extent does sort of democracy give you a different answer to sort of cooperative behavior under these under sort of the initial versus the modified payments. If you just, and in one story would be you just look at sort of how cooperative people are when they vote for a rule versus if the rule was imposed exogenously, and you get this difference here. But the other is to reweight. In this case, you reweight by the population of averages of how people vote, and you get something that's different. Okay? So again, weights came in and allowed us to solve a problem. And it turns out to be a convenient problem in this case because in the previous paper, we even people who had random rules imposed on them had to vote. And in practice, that's kind of a strange thing to have happen. So we can now use this method even in cases where people who have a random rule don't have to vote. Okay, there may be a place in the world where people get to vote and then the government does whatever the heck it wants. But I'm not sure that's the most likely scenario. Okay, so let me just finish up, remind you what we are, but then I'll give a few minutes if there are any questions. Okay, so sort of one of the key insights from this is that the idiosyncratic processes that affect the process of household formation and the pure randoms from sampling matters. Right, our ability to solve this problem in the first case and the fourth case, which I didn't really talk about, has everything to do with this issue. Okay, that the sampling issue is a different problem from the endogenous sort of shocks that we normally think about. And that turns out to be quite helpful with regard to a couple of different questions. Okay? Construction of cross-sectional weights in panel data is going to be really hard without vital registration data or without questions that allow you to figure out how many links you have linking one set of houses to another. Okay? Follow-up strategies matter. We have this ideal. We're going to go and interview as many people as we can. And that's, in some sense, for some purposes, very good, but there are trade-offs that one has to think about. And so I would suggest, we can at least be deliberate about what we're doing there. Okay? And sample sizes and weights matter for spatial heterogeneity. If you're going to look at spatial heterogeneity, you need to realize that sample sizes are a first-order concern, not the usual second-order concern. So let me stop there, and I think maybe 5 minutes. If there are any questions or thoughts or reactions?